Hello and welcome to the second unit on control signals and timing sequence, which is the second unit on the module on control block of the CPU. So, in the last unit basically, which was the first unit on the control unit module, we have discussed that basically how for a given set of instructions, what are the micro instructions involved in executing that macro instruction and what are the basic kind of a control signals required to do it, and we got a very broad idea that how these macro instructions are broken down into micro instructions and they are executed. Basically in today's module, now we will see basically for given each of the micro instructions, what are the control signals required, exactly which block of the CPU generates those signals and what are the timing sequence for that, and we will be understanding that in a more depth or a more what do I say that more in a digital fundamental manner, in which digital design fundamentals using timing diagrams, which signals are generated by which blocks, what are the inputs to the registers in that manner. So, in fact, today we will see how micro instructions are basically executed, what are the control signals in terms of digital design and what are the timing involved in, you will understand the timing sequence using timing diagrams. So, if you look at it, today we are in the second unit of this module, which is on control signals and the timing. So, as we are going in a pedagogical manner, so or a pedagogical form, so let us first look at the unit summary. So, basically we already discussed that the control unit is responsible mainly for generating the signals for data flow within the CPU, that is internal to the CPU data transfer between the CPU and the memory or the IO devices. So, basically in this unit we will be covering what type of signals are required to do that, and mainly we will be taking a very simple architecture, that is a single bus architecture. Also we will see that how basically the different functions of the arithmetic and logic block, like whether it to be added, to subtract, to go for a shift, how signals are generated by the instruction register and how ALU is controlled by that. Then we will see basically, we will also see in a black box manner that what is the control unit, what are the inputs it takes from, it takes basically the inputs from the flag registers, it will also take inputs from the opcode, that is from the instruction register. If you take an instruction which is loaded in the instruction register, basically the opcode decides that what the functionality now the CPU or the control unit has to do. So, basically the control unit will take some inputs from the flags. It also, because for example, if you have a jump instruction, so you need to know what are the previous values of the flags, so it has to read the values of the flags. Then you will also see basically that of the main heart of the control unit to function is the input from the operations that are required to be performed by the opcode of the instructions, and also we need some other inputs to do some functionalities like the control signals which will be coming from the maybe the memory, because when you are sending a data to the memory or receiving the data from the memory, there is a handshaking signal involved, which will actually the signals will be coming from the memory block to the actually your bus. So, basically if you look at it, we will see what are the inputs and outputs of the control unit and what is the output manner where the data comes from, and the basic formats we will be looking into. Then also, as I told you, this was the inputs, also we will be looking at the outputs of the control unit actually that generate signals which will instruct that where the data has to move from, whether it is from one register to another or whether the data has to go from memory to ALU or vice versa. So, we will see basically what are the outputs of the control units and how it basically determines the functionality, like whether there should be an addition, whether there should be a data transfer between memory to register or from register to register, etc. So, we will study the input output functionality and the signals involved in a control unit. That is one of the main part we will study. Then basically we will see what are the very important chunks of signals for that. Of course, very important chunks of signals will be, as I told you, the instruction register. Instruction register, which will consist of the instruction, is the main heart that will actually command the control unit, that this is the opcode of the instruction, now you have to do this. For example, add. So, the opcode for the add, which will be present in the instruction register, will ask the control unit to generate such a signal so that the ALU goes to the addition mode. So, in fact, so the instruction register is a main command mode for the control unit. Then of course, as I told you that if you have to use a jump instruction or sometimes you have to use the values of the flags which was set by some other earlier instructions, may also decide on the functionality of the control unit. That is, for example, if you want to jump on a 0, so you have to also look at what are the results of the previous instructions. So, the flags are also a very important source of signals, control signals as input to the control unit. Of course, then there is something called the control bus, because not only from the flags and instruction registers, also the control unit will depends on signals from the memory, from some IO devices, etc. So, the control bus basically will take care of all this. So, it will ship the different signals from other than the central processing unit like memory, IO devices, and the control unit has to act on that. For example, if you want to interface with a keyboard, when the keyboard is ready to send a signal or ready to then only the memory will be reading your data from the keyboard. So, in fact, the control bus will take care of that. And finally, there is a clock, which is actually the whole synchronization part of the entire control unit or the central processing unit. So, basically as we know, it synchronizes all the module in the control unit, and in fact, we assume that in one clock pulse, one micro instruction is occurred or can be processed. Then basically we say that if you want to chunk out that what are the two different basic classification of the signals, these were all about the input signals like instruction register, flag and control bus. So, what happens actually, your control unit basically takes signals from the clock, instruction register, then your opcode, that is your basically it takes signals, as I told you, from the clock, instruction registers, which is the main, flag and control bus. Using that, it basically generates some output signals. So, output signals can be classified in two types: control signals which are inside the CPU, like for example, you want to add two numbers. So, the ALU has to be commanded. So, data transfer from, so you can select the specific ALU function for the current micro operation like add. So, in fact, if you are saying that specific ALU function, so in that case the control unit will generate some signals which are required only for the ALU to function. So, it is an internal control unit signal. Similarly, if you want to transfer some data register from one register to another, so you need not send any control signal outside the control unit. So, basically this is some type of internal control signals. Of course, the control unit will also generate some controls for the external parts like your memory, your IO modules. For example, as I told you that you want to write something to the memory, you give some address and then you give the data, but then you have to wait till the memory said that I have already read the data, now I am free, because reading the data from the memory buffer register takes some time. So, in that case there will be some control signals, like it has to be generated saying that you start the read, that is the read signal, then sometimes it has to wait till the memory has done the operation. So, basically some of the control signals will be generated which will go to outside the control unit, like to the memory, to the IO modules. In that case they are done through the control bus, because when the control signals are internal to the CPU, then internal to the control unit, or when the CPU, when the signals generated by the control unit are reserved only for the CPU, that you did not go to memory, etc., then are all internal. But if you are going outside the CPU, then you have to talk to memory, you have to talk to other IO modules, etc. So, in that case we go to a control bus. So, so basically that is the input output organization in terms of a control unit. So, what are the basic objectives of this unit? Basically, you will be able to, first is the knowledge objective, you will be able to describe the different categories of input and output signals of the control unit. That if you take a black box of the control unit, then you will be able to tell which is the inputs and the outputs. Next, the comprehension objective, you will be able to indicate the control signals to synchronize the speed of the memory module and the processor. That is how basically a clock occurs, on basis of the clock, how basically other control signals are generated or taken as input by the control unit. So, you will be able to indicate the use of clock and synchronization. Finally, the synthesis objective, you will be able to design timing sequence to carry out proper micro operations at an appropriate time. That is, you will be able to design micro operations and in fact, you will be able to design at the granular level that what functionality or what signals to generate or what signals to expect as input or output at appropriate exact timing of the clock. That means, you will be able to represent or design micro instructions in terms of timing diagrams. So, that is about the basic objectives of this unit. Now, as I was saying, we are coming to the basic idea of the unit. We are saying the general model of a control unit. So, this is a control unit which will be in your central processing unit. It will actually do all the commands to the arithmetic logic unit, to the registers, to the cache memory, etc. So, basically this is your control unit which will take care of all the points. So, the inputs, as I told you, is a clock. The clock is the synchronization block. Everything will be synchronized in terms of clock. As I told you, there will be flags. We have already know there is a 0 flag, non-zero flag, carry flag, etc. So, they will also be input to the control unit. Now, why is flag so important? Because I told you, if you have an instruction say called jump on Z. So, in fact, say that is the instruction register will have the instruction called jump on Z. Now, the instruction register for jump on Z, there is an off code. Say for example, the off code is 111 in this case. So, this input signal 111 to the control unit will specify that it is a control jump instruction. This is not an unconditional jump, it is a conditional jump. So, this input from the instruction register, that is the off code part, because we assume that the jump instruction jump on 0 to some memory location is already loaded in the instruction register. The off code corresponding to that will generate the off code which will actually control the control unit. It is an input to the control unit telling it what to do. So, this is an obvious input to the control unit, that is the off code for the current instruction, and in fact that is the heart of the inputs to the control unit, because that tells you what to do now. Now, the flags. Now, as I told you, is a jump instruction. So, you have to know previously what was my input, or what exactly was the operation done, whether if I have subtracted 2 numbers, whether the answer was a 0. If it is the case, then I will jump, otherwise I will just go to the next instruction. So, the 0 flag has to be set if the previous subtraction operation resulted in 0 operation, or any operation resulted in a 0 operation. So, the flag, if the 0 flag is set, that signal will be sent 0 over here, and the control unit will know that jump on 0 is 1 1 1, that is the off code, and of course 0 flag was set, that is in fact it was 1, sorry, I mean this is set because the answer was a 0. So, 0 flag is set, and accordingly whatever you want to do, such signals will be generated by the CPU. Like for example, in this case you are saying that jump on 0 0 to 3 0 3 0. So, in fact the program counter will be now loaded with say 3 0 3 0. The program counter will be loaded with the operation 3 0 3 0, and you already know that program counter is a register which is internal to the CPU. So, in that case the control signals will be generated within the CPU. Now, the program counter will be loaded with the value of 30 30. So, the control signals generated by the CPU control unit will generate the signals which is internal to the central processing unit. It will be something like it will configure the program counter in a load mode, and you will load it with 30 30. So, in that case simply your next instruction will start from 30 30 memory location. If you take another instruction, let us assume that is a simple add operation. Add, say we call it 30, from the memory location you have to load 30 30. So, in that case what happened? Maybe the opcode of add is 0 0 1. So, in this case the 0 0 1 will be fed from the instruction register to the control unit. In that case flag is not required, because you are just going for a add and you have to load from memory location 30 30. So, it will first generate some input signals to the CPU, that the ALU has to be configured to a add mode. Fine. Then you have to read some data from 30 30. Now, it will generate some data 30 30 which will be fed to memory address register, because you have to read from memory location 30 30 which is to be fed to the memory address register. They are now all internal CPU instructions, but actually you have to also generate a signal called read, because you have to read from the memory. Of course, then you have to also put the memory address of 30 30 in the memory address register, all those things are there. Like, but memory address register is an internal register to the CPU. So, it is an internal signal, you have to load memory address register with 30 30. But you have to make the signal to the memory saying that it is a read signal. So, it will generate some signal to the control bus which will actually ask the memory saying that now you have to go to a read mode. Of course, after that what will happen? The memory will dump the value of 30 30 in the memory buffer register. Now, what happens? Now, you have to wait for certain time till when the memory will load the value of 30 30, or the whatever is in the memory location 30 30 to the memory buffer register. Till that time the control unit has to wait, because immediately it cannot read the memory buffer register. It takes some time. You are giving the 30 30 in the memory address register, asking the memory in a read mode, and then you have to wait for some amount of time till which the memory gives the value whatever is present in 30 30 memory location to the memory buffer register. Once it is done, the memory will give a signal saying that I am done, now you can read the memory buffer register. So, that will be a control signal which will be coming from the control bus, and the control unit will read it. Once this is enabled, then you can read the value from the memory buffer register, which will be again taken by the data bus. It will be going to the accumulator, or and then it will be added. So, basically in this case you can see there are some signals which are for the internal use of the CPU, and there are some signals which is for example memory or IO which are for the external use. For such external use we are using the control bus, and for our internal use there is an internal bus of the CPU like register transfer, transferring, configuring the arithmetic logic unit, etc. So, that is basically the generic model of a control unit. So, as I was telling, now whatever I discussed they are actually written in the text so that you can read it. So, as I already told you, clock is nothing but a synchronization module. As I told you, we have not talked anything about the clock over here, but whenever all the instructions or all the signals are generated, they are all either at the positive edge or the negative edge of the clock. Means everything has to be synchronized with some clock edge. As I told you, instruction register, heart of the control unit. It tells exactly what to do. So, like for example, it is saying load R1 32. That means, whatever is present in the location 32 has to be loaded in R1. As I told you, so the off code corresponding to load will actually direct the control unit to do that. So, as I told you, so it is a heart of the control. There is a flag, as I told already explained, that flag is very important because you have to remember what happened previously. Like for example, if there is a sub instruction and it set the sub r minus 31 may have been 0. So, the 0 flag has been set, but next after that you are using a conditional instruction that you should jump if r1 is equal to 31. That means, whether the value of 31 is equal to the whatever value is in the register R1, if that is set, then you have to say I want to jump to some other location, otherwise I just want to do not jump, I just go to the next location. So, in this case you have to reuse, you have to read the value of flag. So, of course, the control signal or the control unit will require the value of flag signals to take a decision. So, they are also the inputs. And finally, as I told you, there are control signals from the control bus. They are basically which are taken externally compared to your CPU, like from a memory. As I told you, memory is saying that I have done the write operation to the memory buffer register, now you can read. So, that signal will be taken from the control unit. For example, you want to make the memory in a read mode or a write mode. So, the control signals will be given as output in the control bus. So, there is a very important control bus for that. Like for example, here is a printing operation, etc. Now, as we were already telling that these were all the inputs. What are the outputs? Already I have given example that basically the output signals are of two types. Therefore, signals can be within the processor, that is CPU, or they can be to the other modules like the memory or the IO. For example, we are already say for example, there is a instruction code load R1 R2. You can very easily understand that both the registers are in the CPU. So, the control unit will just make R1 into load mode and R2 in the output mode. For example, because registers are nothing but this is one set of flip flop which is R1 and there is another set of flip flop which is R2, because they are registers. The control unit will make it in such a fashion so that this may be Q, I am just assuming a D flip flop, this is D and this is D and this is Q. So, it will make it in such a fashion so that the output of all the D registers of R2, that is Q, will be made connected to the input D of the R1. So, R1 output will be loaded into R2 at the clock edge. So, simple such connections will be done. In fact, by digital fundamentals, if you have forgotten, you should go and read about multifunction register. That means, a multifunction register can do multiple things. It can load from other register, it can load from input, it can freeze its input, it can go for increment, it can go for shifting. So, you have a multifunction register. Basically, this is a register. If it is D, there is a multiplexer over here which actually do lot of interconnections, and then you can set it in the functionality you require. It is a digital design fundamentals. If you have forgot, you can just go and recollect it. But in fact, for this load, what happens? You will connect the multiplexer in such a fashion so that the output of R2, that is Q, will be connected to the D of R1. So, you will load R2 to R1. So, in that case, it is a simple load operation. So, the control unit will generate the signals for the multiplexers of R1 and R2. So, as registers are internal to the CPU, there is no signal to be given to the output in the control bus. Like for example, if you say that add R1 32, in this case, for example, if is a specific instruction, say as I assume that it is an immediate operation. The 32 is basically nothing but you have to add R1 with the absolute value 32 and add it. So, in this case also again, if 32 is a memory operation, then it will be an external signal. But if I assume 32 be an immediate operand, then you have to add R1 and 32. So, you need not generate any signal to the control bus. Only what will happen, add opcode immediate will configure the ALU to be in the read mode, and then 32 will be loaded to the accumulator and you will add it. So, basically for such type of operation like load, data transfer within the register, some immediate mode of addressing, you need not generate any signal from the control unit to the control bus. Like for example, if you say that load R1 32, in this case, as I told you, if 32 is not an immediate operand, it is a memory location. So, in this case, you have to make a control signal read, that in the control bus you have to say that I want to read, then you have to put 32 in the memory address register, but memory address register is an internal register. So, that load command or load signals is an internal load, but the read which is commanding the memory to be in read mode is an external signal. So, that has to go to the control bus, but when memory address register is loaded with 32, that is an internal one, but this is read is an external command to the control bus. Then after some time what will happen, the memory will load the value whatever is available in 32 in memory buffer register. In that case again, the control unit has to read via the control bus, that when the memory has said that I am ready, you can read from the memory buffer register, that will be an input. Similarly, if you have connected an IO bus, obviously control signals has to be read from the IO bus for synchronization. As I told you, for example, if I am using this mouse, then when I am making a mouse click, then your control signal will be read from the control bus by the CPU. It will find out that the mouse click is there, then it will give command for display. So, whenever there are IO devices involved, memory devices involved, which is out of the CPU, then the control bus comes into picture, which is taking signals in and out from the control unit. Now, very important thing, that is, we are going to look at what is the basic architecture of a single unit bus. So, let me zoom it. So, if you look at it, it is basically, again let me just escape. So, if you look at it in a broad picture, so this is a single bus. So, in one part of the bus, this side you can have your, you can assume that there will be an internal bus, there will be some control buses, etc. There will be your memory, there will be your IO. So, all these devices will be there, and this is an internal, and of course, there can be some control bus and several other buses which at present we are not talking about. So, internal control bus means this part is basically nothing but your CPU, okay, and this part is your memory, this part is your IO devices, this part is your memory devices, and in fact, there is a control bus for the synchronization. Now, what we will do? Now, initially we will look into details on all the internal CPU bus, because for the external devices, when we will be covering entire modules on IO, there will be entire modules on memory. So, we will be handling that in details. So, for example, for the time being, let us just look at the details of the internal bus. So, there are some registers R1 to R32 or R64, how many registers you have. So, if you want to take from any input from the register from the internal bus, then what actually you have to do? You have to make Rin enabled, that is Rin equal to 1. If Rin equal to 1, whatever data is available in the internal processor bus will be fed to R1. If it is R1, R2, then we have just drawn it in a single Ri, but in fact, if there are 32, you have to replicate this part in 32 ways. So, but one very important thing is that, so like for example, if I want to get the value of output of Ri to this processor bus, I have to make Ri out equal to 1. So, what happens? Say for example, I have got the value 32 in the bus. Now, what I want to do? I want to read this 32 into R1 and R2 and R3. So, what you have to do? Rin 1 for R1 has to be made 1, Rin 1 for R2 has to be made 1, and Rin 2 for R3 has to be made 1. So, in this case, all the registers will be enabled in a read mode. So, 32 will go to R1, R2 and R3. This is fine, but you have to be very, very careful that Ri out cannot be more than 1 for any block which is giving output to the register. For example, if I say that somehow I make Ri out, that is R1 out equal to 1 and R2 out equal to 1. What will happen? The data from register R1 will also go to the output, and somehow in this case some R1 will also go to the output, R2 will also go to the output. There will be a contention. So, that we cannot have. So, while giving any output to the control unit, one output to the internal CPU bus, we have to be very, very careful that only one register or one ALU or one memory buffer register, etc. is loading into the internal bus. Multiple parties cannot output at a single go in the internal CPU bus. That is very, very important. Now, who takes care? The control unit, because the control unit will generate the signals R1 in 1, 1, R2 out equal to 1, something like that, because whether register R1 is going to read or whether this one or whether register R1 is going to give the output will all depend on the control signals Rin and R out, which will be generated by the control unit. So, control unit very judiciously takes care that no two guys, no two registers or not ALU and register, not memory buffer or register together dumps at the same time in the internal bus. That is, out signal of any register, two registers or one register or a memory buffer register can be one at a time. So, these are all registers organized in this manner. I forgot to draw this. Now again, if I zoom this next part of it, so you can see that is basically the second part is an ALU. So, either you can get the value from Y. So, that is means whatever this is an input from the control bus. Sorry, it is from the internal bus where you can get the data values. So, either you can get the data value Y in. So, it is a multiplexer, the ALU. So, you can get one. As I told you, ALU basically does all the mathematical and logical operation. So, there are two operands for this. So, one operand basically comes from the CPU bus and another operand basically Y is a register. So, sometimes you may have to hold the value temporarily. Like for example, if I say that I want to make add, I want to go for say add accumulator and 32 immediate. So, in this case what is going to happen? Very interesting similarly. So, 32 value, that is what he is saying, that add 32 if you see. So, it can be fed over here by this line, direct connection, because the controller will set in such a fashion. So, the value of 32 will be loaded over here. The control signals also will make the ALU to be a add mode. For example, when I am going going to execute this command add accumulator 32 immediate. So, it will be converted to add mode by the signal, by the signals of the control unit. 32 will be loaded in the bus. So, you will have the value of 32 over here, but previous value of accumulator has to be added to this. So, in fact, actually the accumulator will be loaded in the previous cycle, value of accumulator will be loaded to y, or in some sense you can also think that in my case y is an accumulator. So, basically sometimes this is what is the idea. So, in the first go the value of accumulator will be, or if the accumulator has, if you have to load some particular value to the accumulator, in first case you will be loading the value of the accumulator from memory or some block to y. I am assuming A as an accumulator, and in the second unit clock you will actually add this accumulator with 32. But now you can see the marks over here, because sometimes we require to add some constants also, like program counter. Program counter will be program counter plus 1. So, in this case I have kept the value 4, because I am assuming in this figure, they are assuming that the number of instruction length is 4. Basically, I can also say that I can make this constant as 1. So, why I am making this constant as 1? Basically, sometimes when I have to increment the PC, so in this case what happens, I will make the control unit will make the marks set as this part, that is, so for example, if this was about the add, so if I go for a, so for example, if I say that I want to go for a PC increment mode. So, in the PC increment mode what is going to happen? You have to go for an increment of the PC. So, in this case I will, this is the flow from the accumulator. So, what in this case I will not go by this path. So, what I will try to do is that this is a constant. So, the multiplexer will be set in such a fashion by the control unit that this signal will enable this to go to the ALU. And in fact, so this will be added. Now, the value of PC, so you are going to add it to 1, and then the PC will be, say for example, 1, because this is the chunk of registers. So, for the time being assume it to be the PC. So, in this case what happened? You will enable in such a fashion that this is enabled will be 1. So, in this part now the value of PC will be there. So, the PC will be connected over here. So, now it is not 32, it is the value of program counter, and program counter will be program counter plus 1. So, now after that you can dump the value output here and you can again feed it back. So, that is, again let me clean the whole picture. So, now again let me do it in steps. So, what is the first step? The first step is basically for add, actually I go by this configuration, that the configuration is this. But now for PC to be incremented, let us assume it to be PC. So, first we are going to go for PC equal to PC plus 1. So, what we are going to do for adding, basically we are for adding two numbers or some other operation, we are going to take this path. But actually for the PC, because it is to be incremented by a constant, so what we are going to take this path. So, the marks is set in such a fashion. So, this one or constant 1 in case if the size of the instruction is 1, it may be 4, 8 or 2, what is the size of the instruction, that value will be fed over here. Accumulator is in plus mode. So, in this case we are adding a value of 1, but now it should not be the value 32. So, it is not the case, you should have the value of the PC fed over here. So, what I will do, assuming that this is the PC, I will make this PC out equal to 1. So, the value of the PC will be in this bus. So, now the value of PC is fed over here and addition is done, and then what happens, this is the Z in plus will be made 1, or in other words this is the path to control the output of the ALU to the bus. So, now it is added, PC equal to PC plus 1 is added and it is now waiting over here. Now, here it is PC equal to PC plus 1. Now, after some time what you will do, you will actually, now it is having the value of PC equal to PC plus 1, because now the output is fed over here. Now, after that what you will do, now you will make this as 1, because now PC equal to PC plus 1. So, now it will be loading the value of PC and PC will be incremented. So, in this fashion basically we require a multiplexer for that. So, this way basically if you want to understand what happens basically in this case. So, this is basically the architecture single bus. So, we have some registers which have input and output control, that is register can be fed in, register can be fed out from the control bus. Similarly, this is an ALU. ALU has also the facility, you can load and also you can write out the value of the ALU to the control bus, and we have a multiplexing arrangement. So, in one part of the multiplexing arrangement you can take some operand from the control bus and the other operand is a constant like increment increment by 1 by some other constant value. So, this is in a nutshell a very broad idea of a single bus CPU. So, now we will tell you whatever I have discussed is given in the text. So, I am saying that for each register including the program counter, memory buffer register etc., there are two signals R in and R out. Basically, if R in is 1, the register is going to read from the bus. If R out is equal to 1, R out equal to 1, then it is going to write into the bus. But you have to be very, very careful that we should not basically enable two R outs at a time, then there will be contention, but there can be multiple R ins. For example, if you are saying that move R1 and R2, then what will happen basically is R1 is feeding to R2. So, what is the control unit is going to generate? The control unit is going to generate that R out equal to 1, because R out is going to give the value to the bus, and R in R2 register is reading. So, R2 in should be equal to 1. So, R2 in is equal to 1 and R1 out equal to 1. So, R1 is giving the value to the bus and R2 is reading. So, of course, other things has to be made 0, because R1 out is equal to in this first case. So, R1 out is equal to 1. So, R1 in has to be made 0, that is the case. For example, R2 is reading. So, basically, R2 in is 1 and R2 out has to be basically set to 0, that is what is the idea, very simple logic. Now, we will take some more important basic ideas, other instructions to make it more clear. So, we are taking a instruction called move R132. So, basically what is the steps? What happens? So, let us assume that this is your control bus. Then what happens? Then this is say register R1. So, as I told you, you can read from the register and also the register can be making as an output. This is your control bus. So, either you can read or you can write. So, in this case the 32 has to move. In fact, here 32 is a memory location given the assumption. So, now what happens? 32 is not an immediate operand, it is a memory location. So, you have to read the value whatever is available in memory location 32 to register R1. So, of course, register R1 in should be equal to 1 because you are going to read it, and then basically other steps will follow. So, what are the steps? First step is that the instruction register should give the command or the micro instructions following that. So, what are the micro instructions for that? For example, the value of 32 has to be first loaded into the memory address register. Why? Because the memory address register is going to give the value to the memory, and it will say that I want to read the value from 32, and it will dump the value in memory data register or memory buffer register. And then finally, that is the first step, you have to put the value of 32 in memory register, memory address register, make the signal read, that is the first signal. Then what happens? Then the memory will see the memory address register is 30, whatever value is memory location 30 will be dumped to memory data register or memory buffer register, and you have to wait for some time. As I told you, this signal is called WMFC, control signal that causes the processor to wait for the MFC signal. That it will have to wait for some time. When the processor, when the memory says that I have written the value what was in memory location 32 to the memory data register or the memory buffer register, it will become 1. Then you know the memory has given the data, now everything is stable. Now, the memory buffer register will dump the value to R1. So, these are the 3 micro instructions. The first micro instruction will lead to basically loading the value of 32 in the memory address register. Second thing, it will read the value in the memory data register. Third micro instruction will load the value of memory location in the R1. So, what are the steps? Let us write down the signals and the registers. So, basically let us assume this is your control bus. So, first is the instruction register. As I told you, it is very, very important. The instruction register is the heart. So, what it will load? It will load the value of 32 in the memory address register. So, as I told you, these are memory address register, MAR. So, in this case memory address register in will be 1 and instruction register out will be equal to 1, because instruction register will dump the value of 32 to the memory address register. So, in fact, these are the 2 internal signals, that is R out, instruction register out equal to 1. So, instruction will dump the value to control bus, and memory address register will in is equal to 1. So, it will read the value of 32. Now, the 32 has gone to the memory address register. These are the 2 internal control signals. Now, next what? Next you have that is the control bus. This is your control bus, which is an external control bus. So, the control unit will generate the value of read to the memory, because this control bus is connected to the memory. This is a memory which is an external, but the first 2 signals were internal, this is an external signal. Now, let us go to the second signal. So, in the second signal what happens? It is saying that now after some amount of time the data will come to the memory data register. We know that because already the memory address has been set. So, some data will be coming to the memory data register. This is an internal part or a memory buffer register, whatever. So, as the data from memory location 32 is going to come over here, this in signal I have to make it 1. This is an internal signal. But then you have to wait for some of these are again an external control bus. You have to wait for some of the signal which is coming from the memory, that is called wait for MFC. The signal is MFC, we are waiting for MFC. Whenever MFC is going to be 1, at that point of time basically already MDR is equal to 1 input. So, whenever MFC is equal to 1, then you know that there is a valid data over here. I have already made it 1. So, whatever is the memory buffer register is coming over here. But I cannot immediately read the value in the memory data register. From the memory data register to R1, I have to wait for some amount of time. Whenever MFC is 1, which is an external signal, then again the third microcycle instruction control signals come up. So, what? So, now basically MDR is already 1, signal has come. So, now what is going to happen? Already memory data MDR has already read. So, now if this is your MDR, it has already read. So, now initially it was in was 1 because it was reading from the memory. Now, it has to make it out. So, memory data out signal is be 1. So, out signal is equal to 1 because already we know that the memory has dumped the value in the memory data register and it will read to R1. So, this in signal has to be 1. So, the memory data will be given over here. So, again in this case these are the two control signals generated, memory data register out equal to 1 and R in equal to 1. As both are registers basically they are all internal signals. So, this is how in a single bus memory operation, that is reading from 32 into R1 works. So, basically what I have told is written in the text over here, which you can go through. Now we are going to look at in a timing, as I told you that we will be all discussing it in terms of timing sequence. So, let us look at the timing sequence. So, this is your clock and we are doing everything in the positive edge or in the positive edge of the clock. So, this is the positive edge, this is the positive edge and so forth. So, first as I told you, first what? Read R1 32. So, what you have to do? First you have to read the value of 32 from the instruction register to the memory address register. So, what I am doing? Just after the first clock edge, I am making MDR equal to 1 and R out equal to 1. So, what is going to happen? R out, that is instruction register which is containing now the memory location 32 will be dumped to memory address register. So, I have made both the control signals equal to 1. So, in the next clock edge what is going to happen, that is the synchronization. At this clock edge what is going to happen, the value of 32 from instruction register will go to the memory register. That is at this rising clock edge the value of 32, at this rising clock edge the value of 32 will go from instruction register to memory data register. It will happen at this clock edge. So, now again let me erase this and let us study the future, in future what happens basically, that is the first clock edge. Secondly, so already we have seen that in this clock edge the value will be dumped. So, we have actually given the value of address 32 has gone to the memory data register. So, in this clock edge has gone, this address of 32 is now loaded into the memory buffer register, sorry memory address register. Now, already we know that we have to give a read signal. So, anyway I have given the read signal over here, you could have also given the read signal over, I have given the read signal initially. So, now at this clock edge these 32 is loaded in the memory address register as well as the read signal is a 1. So, now the memory is configured that in this case in this clock edge the instruction register has given the value of 32 to the memory address register, which is this case read signal was already 1. So, now the memory knows very well what it has to do. And in fact, already I have, so this is happening in this clock edge. So, by this clock edge the memory data should come, because in this case I have sent the value 32 to the address register in this clock edge that works, and again in this clock edge the value of 32 will be taken in by the memory and the read signal is also 1 at this place. So, in fact, now it will start dumping the value of the memory data register in the memory register, in the memory data register, the memory will start dumping the value whatever is in 32. That will actually happen in the next clock edge. In this clock edge it should start happening, because in this clock edge 32 is loaded, in this clock edge because everything happens in positive clock edge. So, if you find in the first clock edge nothing happens, in the second clock edge basically in this edge the instruction register value has gone to MAR address register, and in this clock edge 32 is loaded in that case and read instruction is also 1. So, in this memory in this memory, in this clock age, the memory is fully configured to deliver the value of memory location 32 to the memory data register. Already read signal was there, and if you see MDIR in was already set. So, now in this clock pulse if you compare, the value will be, after this clock pulse, that is this clock pulse, the value will be fed to the memory data register because the signal is already 1. And only after this the MFC signal will be set as high. So, what is this MFC signal? Only after this clock pulse the MFC signal will be high, means it will say that now I have done the value of memory location 32 in the memory data register in a very peaceful manner, everything is stabilized, now you can read. So, that is the signal. So, that will happen in this positive clock age. And after that has happened, that MFC has been given as out. So, what you will do? This says that I have done or I have given everything which was in memory location 32 to the memory data register. Now, what you will do? Now, we have to read the value of memory data register to the register R1. That is, you have to do this part, that memory data register value will have to be dumped to register R1. So, only after that MFC signal has become 1, you can make the memory data register signal as out, because before that if you see the memory data signal was a 1 over here, in 1, that is memory data register in was a 1, that means it was reading from the memory. This MFC signal is saying that the reading is over. So, now you make memory data register out signal equal to 1, that means now it will dump the value whatever was in the memory data register which is taken from the memory to the bus, and then R in 1 equal to 1, that means whatever was in the memory data register will dump to the register R1, and this instruction of move R132 will be over. So, if you can recollect it, look at the figure in a slightly you can think it for some time, then everything will be very clear to you. Then this was a move instruction. Now, let us say that is a store instruction. Move means what we have done, we have taken the value of memory location 32 whatever was there, we have moved to R1. Now, let us very quickly see that if this is the reverse one, that is if there is something in memory register R1, sorry, if there is some value in R1, we want to dump it to memory location 32. One was the read operation, next was the write operation. Very simple. Of course, first the value of R1 has to be written to 32. So, the register value R out instruction register has to be made 1, because the default idea is that whatever instruction is there will be first in the instruction register. So, for any instruction in a general thumb rule, what is there? You have to first make the instruction register out. That means the value of the instruction register has to go to the memory address register, because whenever there is a non-immediate mode of operation. So, what happens, like in this case the memory location is 32, that means you have to do something with memory location 32, but where is that value 32 will be there? In the very initial case it will be in the instruction register. So, generally the first micro operation always says that the instruction register out, that means you have to get the value of the memory location from the instruction register, and it has to go into the memory address register. That is a very de facto standard for most of the cases. So, the value of 32 from the instruction register will be dumped to the memory instruction register. Even if you have looked in this solution also, the same read or write from the memory, the first micro instruction will be more or less similar. So, the first micro instruction instruction register out will dump the value to the memory register and memory address register. That means, instruction register 32 value will be now dumped to the memory address register. So, now the memory address knows that value of 32 is there. Now, we have to do something with 32. Now, in this case what happens? You have to write. In the previous case what happened? It was a read. Now, it is basically a write. That means, whatever is in the memory, whatever is in the register R1 has to go to the memory. So, now in this case what happens? This is the memory. This is 32 memory location has to be read, and in fact, there is a memory data register. So, in the read mode from the memory data register has to be read, but as a write operation, so you have to dump the value of here. So, in this case it will be just the reverse compared to the previous analysis. So, MDR will be actually equal to in. So, now the memory data it has to read. So, the memory data register will be in a read mode, because it will read something from the register R1 and that has to be dumped to the memory. So, in the previous case memory data register in was a 1. That means what? Basically what happens, again as I was telling you, that the first micro instruction and the second micro instruction more or less look similar in case of a read write mode, because in any case memory data register is to be read, either it is from the memory or it is from the CPU register. If you are going for a read operation, then the memory data register will read from the memory. If you are going to go for a write operation to the memory, it is going to read from the register. But anyway, memory data register has to read some value which is to be transferred to the memory, or it has to be transferred to the register. So in this case, memory register data register is equal to 1 and R out equal to 1. So in case what happens? In the second case, so if you look at it, so this is your register, memory data register, which is in mode, and your register R1 is in the out mode. So the register will dump the value which will go to the memory data register. But this is a memory write operation. If it is a memory read operation, then actually in fact it will not be a R1, in fact it will be a memory which will dump it to the value to the memory buffer register, which will go to the memory. That was the previous case. But in now second case what happens? Memory data register is in mode, and who is going to write it? The instruction, the register R1. So R1 will be out will be 1. So in that case it will be going in this case. And very important, we have to know one point over here which I want to emphasize. Basically, first micro instruction R out equal to 1, that is you are dumping the value of 32 to the memory address register. Before going to the second micro instruction, R out, IR out has to be made to 0. Otherwise, what is going to happen? Otherwise, there will be a conflict. Both the instruction register as well as R1 is going to write together to the CPU bus. That should not happen. Before going to the value here, this has been made 0. But now in this case, R out is 1, this one is in is 0. So basically, now R out is going to write to the memory data register. And now we are giving a signal called write, because the memory has to be in write mode. Now what happens? So now your memory data register already has the value which is in the register. So this phase is over. So last micro instruction, basically it will do, let us see what it will do. This is your instruction, this is your bus. Now your already memory data register has the value which is from R1, and also you have given the write command. The write command is basically an external signal, all others are internal signals which is generated by the control unit. Now memory data register out is equal to 1. So now it will start dumping the value. Now of course the memory is already in the read mode, and memory data register is writing to the, this will be a control bus, or sorry, in fact it will be the data bus, which is an external bus which will be connecting the CPU to the memory, and already the write signal is there. But immediately you cannot withdraw this signal. Memory data out has been made 1. So the memory data register is writing to the control bus, but immediately you cannot make the memory data out equal to 0. You have to wait for some amount of time. Through an external bus, external control bus, the memory will tell that MFC, that is going to come by a external control bus to the CPU, telling that my read is over, or sorry, my read is over. That means I have already read the value of register R1 in my memory location 32. Now you can free your memory data register. After that case only, your memory data register output will be made 0. In fact, initially it was 1. So memory data register was dumping, which was going to the memory. After some amount of time, when this WFMC signal will be coming from the external control bus to the CPU, sorry, to control unit of the CPU, it will relinquish the signal, and MDR out will now become equal to basically your 0. Now it is freed, and whole value of R1 has been dumped to memory location 32. So again I will quickly look at the control sequence, because it is more or less similar. So in fact this is the positive edge of the clock. First instruction register has to be R out, will be 1, same procedure. In the next clock edge, as memory address register is already 1, so the value of 32 will be dumped in the address. From here it is slightly changing because it is a memory write operation. Now R out in equal to 1. So now from this, at this clock edge, basically as I have made this memory data register in 1 at this point, at this clock edge what is going to happen is that the value of the register R1 will be out to the control bus, and already memory data register in has been made 1. That means at this clock edge, at this positive clock edge, what is going to happen? The value of R1 will be going to the memory data register in. Now memory data register in will be fed with the value of register 1, but where the memory data register will write? To the memory which is in the memory address register, which is the value of 32. So R1 out will make the value of register R1 being dumped to the bus, which will go to memory data register, and memory data register will write the value. That is what it is saying, that the data is whatever is in the R1 data has moved to memory data register, which is happening in this clock edge, and this memory data register will be writing it to the memory. So the memory write signal has been made 1. Now at this clock edge, basically as I told you, at this clock edge the data of R1 has been moved to the memory data register, write signal has been enabled. So, now I am making the MDR equal to 1, that means now the memory data register is going to write to the memory. So, I am making the memory data register from input mode to output mode, which I am making it 1. So, in fact, at this clock edge, if you compare, this is the rising clock edge after this signal, after the MDR signal equal to out, this is the clock edge. At this clock edge, your memory will read the value from the memory data register, because memory data register out signal equal to 1 and we are in a write mode. So, at this clock edge, this is the positive clock edge, your memory is going to read the data from the memory data register. But again, immediately we cannot make MDR out equal to 0, we have to wait for some amount of time, when the MFC signal will be say memory has been written. So, after this clock edge, basically you can, again I have not shown this, but again you can, in this point you can make this signal down over here. This signal can be made down at this point, because there is no point of keeping the value over here. So, simply the memory has been written. So, that brings us to the end of this unit. We have taken a single bus architecture and we have taken some very simple instructions, which are macro instructions. We have broken down into the micro instructions and we have seen what are the basic micro instructions or what are the control signals generated and how data transfers operates, happens between one register to another register, one memory to another memory and via register. And also we have seen that if you read to a memory, if you write to the memory, what are basically the control signals involved. So, in fact, in a nutshell, today we have got some idea using a very concrete digital fundamentals how basically a control unit works in terms of signals. So, before we close down, as we all discuss about some of the questions and try to understand how the objectives are satisfied. So, let us take some few examples, like provide a generic model of the control unit, explain the groups of input output of the signals and give some examples. Of course, this will satisfy your knowledge objective, like different categories of input and output signals. As a comprehension, you should be able to design the as a comprehension objective, you will be able to indicate the control signals to synchronize the speed, etc. So, if you are able to answer the first question, that what are the different signals, these two objectives are satisfied. If I ask you to draw a CPU with a single bus organization, of course, this will again satisfy the next two objectives. Then in this question 2, we have some parts, we are saying that how registers are connected to the CPU and how basically signals move over there, and then we say that how they are synchronized in time. So, if you are able to design a single bus CPU, then you explain how data is moving from register to register, register to memory, and how they are all synchronized with time. As we have said that everything happens at the positive edge of a clock. So, even if I have changed the signals like R in out, data memory buffer register is equal to in, but they will all take effect in the next coming edge. So, if you are able to design that, of course, you are going to satisfy the synthesis objective, that is design the timing sequence generator to carry out the proper micro operations at a proper time. So, in fact, if the 4 questions if you are able to answer, you are going to you are actually meeting all the objectives. With this, we come to this end of this unit, and from next unit onwards, we will be looking more into depth of how control signals are generated, if there is multiple buses, what are the changes expected and so forth. Thank you.